If you're an NVIDIA Cloud Partner, an NCP, or a GPU as a service provider, this presentation and demo will show you how to build a hyperscaler grade GPU cloud with Aarna. The GPU as a service market has been in hypergrowth. There are many market research studies. This particular one predicts that the growth of GPU as a service providers will be 10x from 2023 to 2032. The good news is you are competing in a great market. The other companies in this space have tremendous revenues and amazing enterprise value, and you can get the same. Having said that, there is no free lunch. The NCP space is undergoing tremendous competition. This is a research chart by Jensen Huang, CEO of NVIDIA, which shows all the NCPs that they've signed up. This doesn't even show GPU as a service providers that are smaller than NCPs. There is tremendous margin pressure. Bare metal instances per GPU as of today have already dropped to $2.30 per hour and continue to drop. New GPU platforms are also emerging. The tech stack is complex. There are many choices that you could be making, and sorting through all of that is complex and confusing. And the clock has started. Your competition is running forward. There are already many GPU as a service providers, including the hyperscalers, and new ones continue to come up. So, time to market is of the essence. Now, you might be thinking, why don't I just do GPU renting or hosting, which is a very static manual allocation per customer, and be done with it? Why do I need to do anything more complex? The reason for that is if you do only GPU rental, meaning you manually configure static allocations, we have a TCO calculator that shows that this will result in at best, a poor ROI and at worst, a negative ROI. So, what you need to do is you also need to supplement the traditional hosting business with a GPU as a service offering. So, GPU rental needs to be supplemented by on demand, self service, hyperscaler grade GPU as a service offering, and that's necessary for a decent ROI. So, what is a hyperscaler grade GPU as a service solution, which is the only answer in this case? On the left hand side, we show what a GPU rental looks like. An end user shows up, they order a large number of GPUs for a long duration, say 1,000 GPUs for 1 year. Then a human being will configure, allocate, provision all of those GPUs statically using manual methods. And sometime later, they'll say done, and the end user will be up and running. A hyperscaler grade GPU as a service offering looks different. It's on demand, it's self service. So the end user could say, I want 1,000 GPUs, but just for 1 week, not for a year, just for 1 week. So short duration. Obviously, you can't be provisioning that manually. So the software, GPU as a service software, needs to respond back immediately, provision, and then respond back immediately. Or you may want very small amount of GPU capacity for a small duration. Obviously, that also can be provisioned manually. That has to be through the software. Finally, you may want a small GPU capacity for a long period of time. Even that, it's impractical to provision that manually. So for all of these reasons, a hyperscaler grade GPU as a service offering is the only answer. GPU as a service providers have some requirements. They need software to convert a piece of hardware into a service. Specifically, GPU as a service providers require hyperscaler grade, self service, on demand GPU as a service, which could be virtual machines, bare metal instances, Kubernetes, with full isolation of GPU, CPU, network, and storage. Uh, GPU as a service providers are unable to find a standard solution. VMware and OpenStack do solve this problem of multi-tenancy and isolation for the CPU world, and to a degree, they address GPUs as well, but they don't really solve the problem for the full GPU ecosystem. GPU as a service providers have bespoke configuration needs. They might want to change networking, they might want to change storage. And finally, GPU as a service providers, if they do have any resources that are available, developers, then they want to direct those precious resources to platform as a service and software as a service layers, which means model as a service, RAG, vector databases, LLM ops, instead of spending those precious resources on the infrastructure as service layer, which is provisioning of GPU instances. So the right hand side summarizes it. At the bottom, you have the GPU hardware. Above that, you have low level hardware provisioning software such as Redfish or NVIDIA Base Command Manager. And above that, you have a gap. And that's the gap that we as Aarna Networks fill. And that's the demo we will show you. And that software also needs to expose APIs, northbound APIs, which we'll talk about. If you double click, what are these GPU as a service gaps? They are in four categories. First and foremost is instance creation. Those instances, GPU instances, could be virtual machine, they could be bare metal as a service, or they could be third party container as a service or Kubernetes add on. You need full multi tenancy, role based access control, RBAC, and as we have discussed, isolation in terms of network, InfiniBand, storage, GPU, and CPU. The tenants need observability of their GPU instances. Next, we need northbound APIs. The tenants or users need to be able to manage the lifecycle of their instances, create instances, terminate them, etc. The GPU as a service provider needs APIs to the BSS system for billing and tenant management. They also need APIs to the OSS system for global monitoring. So, global observability is different than tenant observability. The tenant needs to see their own instance, GPU instance, while the GPU as a service provider needs to see the status of the entire hardware infrastructure that they own. Last but not the least, to get a positive ROI, any unused GPU cycle must be monetized. Anything that's left idling is basically increasing the return on investment by that much more. The right hand side summarizes what we just discussed. The hardware provisioning, and global observability comes from vendors such as NVIDIA. It could come from others. The operating system, KVM, and Kubernetes layers come from third parties as well. But the GPU drivers and the operators have to be provisioned, and those are gaps that we fill. We also fill the above gaps in terms of multi tenancy, tenant observability, instance creation and management, and northbound APIs and GUI. These requirements can be solved by the Aarna multi-cluster orchestration platform, or AMCOP, which is an open source orchestration and management platform based on Kubernetes. AMCOP 4.x is now available for production use. There are other presentations that explain this block diagram. So in interest of time, we are not going to do that today. But in terms of functionality, AMCOP can orchestrate and manage virtual machines and bare metal instances across tens of thousands of GPU sites or factories. AMCOP can orchestrate and manage the Kubernetes layer, overlay networks and applications on top of this infrastructure. It can provide monitoring with open and closed loop automation, active and available inventory management. AMCOP 4.x is based on proven open source projects, specifically Kubernetes. RBAC, role based access control, and multi tenancy is baked in. The GUI is skinnable, and there are northbound APIs available per use case. This shows a more detailed diagram of the solution. So at the bottom, you have the GPU hardware. It could be NVIDIA DGX, 8GX, MGX systems. On top of that is a hardware provisioning layer, such as Redfish or NVIDIA Base Command Manager. On top of that, AMCOP provides the multi-tenancy and isolation layer in terms of multi-tenant instance creation and lifecycle management, GPU, CPU, network, storage, isolation, usage metrics, and finally, northbound GUI and APIs. The APIs can go to the user in terms of cloud-like APIs to manage instances, or they can go to the OSS BSS system. Now we are going to get into the demo. The objective of the demo is to show three personas. the NCP or the GPU as a service admin, and two tenants, tenant 1 and tenant 2. And what the NCP admin is going to do is to onboard GPU hardware, create two tenants. Tenant 1 will then create two GPU instances. Tenant 2 will do the same, create two GPU instances. And then we will show the observability part. And last but not the least, we will show that there is isolation. Uh, we will show that the instance of tenant 2 can talk to each other, but instances of tenant 2 cannot talk to instances of tenant 1. And implicitly, we will also show you GPU, CPU, InfiniBand isolation, uh, and just give an overview of storage isolation. The sequence of the demo is we'll have a pre-demo setup, we'll have NCP admin tasks, tenant 1 tasks, tenant 2 tasks, and then we'll verify isolation. Specifically in the pre-demo setup, we will show you that AMCOP is already installed, the GPU server is already provisioned with the operating system and the right drivers. This is very time consuming, so we are not going to show this in the demo. Step 2, the NCP logs in and creates two tenants. In terms of the roadmap, this will be done by the BSS using northbound APIs. We will show how to onboard a pre-provisioned GPU server and check that it shows up in the global inventory dashboard. Step 3, tenant 1 logs in. Tenant 1 creates two GPU instances. These are virtual machines, Kata containers. And we will also show you the tenant observability or the tenant dashboard. Tenant 2 does the same. And the last or the fifth step is we will SSH into VMs of one VM of tenant 2 and show that it can communicate to tenant 2's first VM, but it cannot communicate to any of the VMs of tenant 1. We will also show you InfiniBand isolation settings. With that, please enjoy the demo. We will first log into AMCOP as the NVIDIA Cloud Partner, NCP, or the GPU as a Service admin. The first task is to onboard a hardware server, a GPU server. In this case, we are onboarding an already provisioned MGX GH200 Grace Hopper server. In a production system, this could be automatically discovered through a lower level hardware provisioning system like NVIDIA Base Command Manager. But in this case, we are adding the GPU nodes manually. Next, we will create two tenants. We are creating tenant 1 and then tenant 2. This is being done manually. In a production system, this could be done through the BSS system using northbound APIs that AMCOP exposes. Both the tenants have been created, so now the admin can log out. Next, we log back in as tenant 1, and as tenant 1, we will be creating two GPU instances. So let's go ahead and create the first GPU instance. So we'll add a new node, give it a name. It's an NVIDIA H100, and the rest of the choices are very similar to what you would pick in, say, a public cloud, vCPUs, memory, etc., operating system. Now we'll pick node 2, and the operating system will come with all the relevant GPU-centric drivers, so the operating system is fully usable in a GPU system. Now we'll look at observability, what a tenant sees in terms of observability. So let's look at the network. The network page shows the public IPv4 address, the InfiniBand P key, and the VNI, private IP address, and the VNI. The VNI is VXLAN ID, and InfiniBand P key and VXLAN are used for network and InfiniBand isolation. Here you see metrics, the GPU metrics that a tenant would see, and now we log back in as tenant 2. So the tenant 2 is going to do the same thing. We'll create two GPU instances. And what's happening underneath as we create those instances is kata containers are getting created. And through kata containers, we get CPU isolation. Through mechanisms such as MIG, which we use, we get GPU isolation. And we already talked about network and InfiniBand isolation. And we have storage isolation as well. So you get instances that are fully isolated. So if there are two tenants, there is nothing shared between them. So both the nodes are, the second one is coming up. Now both are running. We can look at observability again. So network parameters, public, private. Well, first we are looking at some KPIs, GPU KPIs. Now let's look at the network attributes, public, private, P key, and VNI. And now what we are going to do is we are going to log into the fourth instance we created, which is the second VM for the second tenant. So we are going to log into it. And now we are going to ping the first instance for the tenant 2. So since both the instances belong to tenant 2, they should be able to communicate, and we see them able to communicate. So that works. Now we will get the IP address for one of the instances of tenant 1, and now tenant 2 will try to communicate to the instance of tenant 1, which of course should fail because they're fully isolated. So let's see if if the ping actually fails. So we get the private IP address for node 1, which is the first node of the first tenant, and we try to communicate with it, and the ping fails. So we have shown that the two instances are fully isolated. Thank you for watching our demo and presentation. If this is of interest to you, please do connect with us. Thank you.